We will discuss today the concept of convergence of a sequence. Convergence of a sequence, and that it was the end or in the middle of the lecture. We will establish the relation between this new concept of a sequence. There is a convergence of this behavior. This is a behavior of a sequence and the boundedness of a sequence. Let me first give the formal definition. Uh, let xn be a sequence of real numbers. Of course, we are considering only the sequences which are sequences of real numbers, and x be a real number. Then we say that this sequence xn converges to this real number x if for every positive number epsilon we can find a natural number or a positive integer, but this positive integer may change according to the choice of epsilon, so it is dependent on epsilon such that the terms of the sequence become come closer and closer to the point x, and that is to say that the distance of the nth term of the sequence from x is less than epsilon for every n after k. So we have this thing. Now let us try to see it in some different or in a different interpretation also. When we say this thing, saying this distance of xn minus x is less than epsilon is equivalent to say that this happens whenever you have this x minus epsilon less than xn less than x plus epsilon and greater than or equal to k epsilon. Look at this remark. Now you see this is equivalent to say that this nth term of the sequence is lying inside this open interval x minus epsilon and x plus epsilon, but this open interval is nothing but this is the epsilon neighborhood of this point A. So we can also interpret this convergence of a sequence in the following way that uh, that let me record it as a theorem indeed first that a sequence uh, here we have found this to be epsilon neighborhood, but in theorem we talk about the arbitrary neighborhood of x. Indeed, that is true for there. A sequence of real numbers is convergent. Is converges. Is better to just say still that it converges to a real number if and only if for every or for each, that would be a proper, but anyway, for every neighborhood u of x, there exists a natural number k, which might also depend upon u. It might change with u also. So I will write it in bracket u just to signify that the dependence, just to focus on the dependence of k, natural number on neighborhood u, such that after kth term, every term of the sequence sits inside this neighborhood for every n greater than equal to k. So now we have this. You can first look at this geometric interpretation, just intuitive. It's not the final thing that you may have, but it says that a sequence is convergent to a some point, and let that point be somewhere here. It's not, and it says that if you consider any neighborhood of this point, let us consider a particular delta neighborhood, and let this be some delta neighborhood, or instead of delta, is better to talk about epsilon neighborhood. And so then this convergence says that for this neighborhood, for this choice of neighborhood, you will be able to find a number, let that number be k, such that after k, for every natural number n bigger than or equal to k, the corresponding term of the sequence has to be inside this neighborhood. It cannot go outside, it has to be inside this neighborhood there. It has to be there. So the only thing that the only possible terms that remain outside this neighborhood will be, for example, in this case, you have x1, x2, so on up to xk minus 1. So these are only the finitely many terms, and possibly they may remain outside of this neighborhood. Otherwise, every other term of this sequence is lying inside this neighborhood. So if you have this kind of phenomenon, then this behavior of a sequence is usually known as convergence of the sequence. So let me first establish equivalence with this neighborhood convergence of the sequence, and then we will uh, work on other things also. Let me look at the proof of this theorem, and first let us suppose that this sequence xn converges, suppose this sequence converges to real number x, and let us choose u be a neighborhood of x. Then by the definition of a neighborhood, we will have some neighborhood, epsilon neighborhood maybe, then that lies inside this neighborhood u. Then there is an epsilon neighborhood, and let that neighborhood that is, I will use the notation, the standard notation that I have referred already. There exists a neighborhood, epsilon neighborhood of x, such that this neighborhood lies, such that this neighborhood sits inside this neighborhood u. This is the definition of neighborhood u, that I mean this neighborhood. A superset, a set is a neighborhood of a point if that set contains epsilon neighborhood or delta neighborhood of that. Okay. Now, since this is a epsilon neighborhood, so epsilon is a positive number, and now you use the definition of a convergence, and the definition of convergence says that for this choice of epsilon greater than 0, we can find, since the sequence is convergent, we can converge, since the sequence is converging to x, so we can find a number, positive number, such that the distance of the sequence, terms of the sequence from x will be less than epsilon 3 and greater than equal to this number k. Now, when you say that this distance of nth term from x is less than epsilon, this is equivalent to say that this x n, the nth term, belongs to this epsilon neighborhood of x, and they in turn this neighborhood sits inside. It is a subset of u, so is in u, and this holds for every n greater than equal to k. So that is each term of the sequence except finitely many are, 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 are inside, are contained in this neighborhood u. So the direct part is quite clear now. So let's look at the converse. For converse, we suppose that for every neighborhood of a point x contains almost all terms of the sequence except finitely many, and then we will prove that then such a sequence converges to the point X. For the converse, uh, for the convergence, no, I have to establish that the sequence is convergent now. For the convergence of sequence xn, in the case where you assume that when each neighborhood u of x contains all but finitely many terms of the sequence xn. So let us consider epsilon a positive number. Then you can see that this set, which is nothing but which is just the epsilon neighborhood of the point x. So if it is an epsilon neighborhood, then you know that every epsilon neighborhood is also a neighborhood also which is by definition of a neighborhood. So this is a neighborhood of x. Hence, by hypothesis, I will have a natural number depending upon u. It will depend upon epsilon. Obviously, it depends upon u, and u is defined by using epsilon, so it will depend upon epsilon such that each term after this number k is lying inside this neighborhood. Look, this is what the definitely what is the hypothesis. But u is what u is this open interval with endpoints x minus epsilon at x plus epsilon. So when some xn is a part of this neighborhood means that x minus epsilon is less than xn, which is less than x plus epsilon, and this is equivalent to write xn minus x is mod of xn minus x is less than epsilon, and you know it holds for every n greater than or equal to n epsilon. And hence, this proves that this sequence is a convergent sequence. So this is the equivalent definition of a convergence of a sequence using the neighborhoods of a concept of a neighborhood. Before we some examples of convergent sequences, let me set some notation. If a sequence xn converges to some real number x, then xn is said to be convergent sequence to be convergent sequence, and the number x to which the sequence converges is called the limit of the sequence. Limit of the sequence. Also notationally, we write this convergence as limit n goes to infinity, xn is equal to x, or we may refer xn converges to x as n goes to infinity. So notationally, we will be reserving these limits, and this converges is called the limit of the sequence. Okay, we have this thing.